Good morning, class. You're welcome to today's lessons. My name is Engineer Joshua. As you can see, I'm here to talk on electrical principle. Electrical principle. Principles. When we talked about electrical principles, it's a module we have tagged electrical principle. So basically, when it comes to electrical installation works, there's what we refer to as what? Design. In designing, before you can carry out electrical work, you have to what? Design. In designing, it has to do with some basic theory or theories in electrical. And of course, calculation. Calculations. Because in designing, some persons just looked at calculation as a normal. If you don't get it right, there is no way you can, in real life, you can get it. So that is why the principal aspects that has to do with electrical, we looked at, which is the design. For those of us that have carried out some works, you must do some mathematics. And in that aspect, we target what? Electrical principles. And one of the lessons which I'm considering has to do with what? Basic circuit theory. The basic circuit theory. When we refer to basic circuit theory, it is the theory behind insulator, conductors. What is a conductor? What you understand as what? An insulator. Okay? Okay? Basically, we have it. So we looked at atom, what is an atom, what is a matter. These are things that basically we know and all that. But you can have them in your materials. But what we are concerned here, because this is aspect of what? Designs and what? Installations. We looked at a conductor. What is a conductor? Of course, we know a conductor. Conductor basically is what? Material. Medium through which what? Voltage or current pass through. A material that contains what? Electrons. But we don't want to go into the theories behind electrons, protons, and all that. What flows in conductors is what? Electrons. And we know that electrons, we say electrons are what? Negatively what? Charged particles. But when it comes to real life, when it comes to current, there's nothing like what? It is what? Life. We refer to it as what? Life. When we are dealing with what? AC. Life. Or in DC, we say positive. Abi? We say positive and what? And negative. Positive and negative. And of course, you know positive is negative is this. But in the theory, it is electrons that what? Moves. Okay? And materials that allow the flow of electrons, we refer to them as what? Conductor. The materials that allow the flow of electrons to move through it easily, we refer to it as what? Conductor. And the material that does not allow the flow of what? Current or electrons to flow through easily is what? An insulator. An insulator. So basically, these are materials whose electrons are held firmly. They grip. Because they do what? In the nucleus, they hold electrons. These are materials. It can be in form of insulator. The cable, the insulated part you can touch freely. You can touch freely. Is what we refer to as what? An insulator. While the part, the cable part, you see that in our practical class, that you can't touch. We refer to them as naked. Naked cable and all that, like the overhead cables you see that doesn't have an insulating or what element is referred to as what? A pure conductor. It allows the flow of current to flow in it. All metals are what? Conductors. And some examples include what? You have examples of the conductors, We have copper, we have aluminium, we have gold, silver, depends. Different types of materials that we're going to see. And of course, we have uninsulating materials like the plastic. You can talk about porcelain, you can talk about glass. These are materials, paper, that doesn't allow ceramics. These materials doesn't allow the flow of what? Current to pass through them easily. Then when it now talks about electrical principles, we looked at what? The SI units. Another SI units. These are standards we have. We have the quantity, we have the basic unit. What is an SI unit? When we talked about SI units, it's a system international, it's a French word. But the way we say an SI unit has some basic units, like you can talk about length in what? Meter. This is what? A basic. Basic units. You can talk about time in seconds. It's measured in what? Seconds. You can talk about mass in gram or kilogram. Of course, we also have, can be in gram or what? Kilogram. We can also have some derived SI units. There are some derived SI units, like velocity, which has to do with derived SI units. You have velocity, which is measured in meter per what? Per seconds. Meter per seconds. We have acceleration, which is acceleration, that is in what? Meter per second square. So all these are basic units that we can see in the material that we have different types. Then these can be derived to combine. They form the what? The SI units. So we have basic, and of course we have the derived SI unit, like we have seen in some. Then of course, in this SI unit, of course we have some that when you talked about measurements, like these are basic units and standards, what it means that we're going to be using. We can have some micro, as a preface, is referred to as what? 10 raised to power what? Minus 6. Refer to it as 10 raised to power minus 6. We have nano, we have mega, we have kilo. All this basically we're going to be what? Using. When we say kilo, kilo is what? 1,000. Kilo is 1,000. Mega is what? Million, as it implies. Nano. So all this basically we're going to be making use of. This, then we have a milli around that, minus 3, whatever you call it. So basically this I will see more in the material. Pico, whatever. As we progresses, we'll see them in the effect, what they are used for, the application of these various prefix and what it means. So let's look at one, force. Of course, we know this in our basic physics. Force, we said, is measured in what? In Newton. Force is measured in Newton. And force F is equals to what? Mass times what? Acceleration due to gravity. Mass times acceleration due to gravity. And of course, we say gravitational force G is equals to what? 9 points. Basically, we say 10, but 9.8 something, whatever, 1 meter per what? Seconds square. Acceleration is a standard unit. You can approximate to 10 meter per seconds unit. This is a standard. Don't ask me how. Okay? So basically, we use this in our designing work. That is how to do with force. Force is mass times what? Acceleration due to what? Gravity. Taking acceleration due to gravity to be what? 10 or 9.81 meter per second square. Then you can either calculate for the mass or the force. Then we looked at another, you see more work, examples and exercises in the material given, which you are going to work on. We looked at what? Work. What is work? Huh? What is work? What is the unit of work? Unit of work is what? The unit of work or energy is in what? In joules. Depends on. Unit of work is in joule or energy, as you can see. Where 1 joule is what? 1 unit meter. 1 joule is equivalent to what? 1 unit meter. 1 joule is equal to 1 Newton meter. And of course, if you say Newton here, this refers to as what? The force. This force is measured in Newton. You can draw this to that. Okay? So we'll see more of example when it comes to work. Work done of the body is in joule. You can see that is where you have to do like what? Work is now what? F S. This already is Newton meter, which is meters second square. Press adapt. Then we looked at power. We looked at power. All these work examples and exercises are in the material. Are in the material for you to carry out some work. Look at power. Power, basically, when we say power, symbol is what? P. Power is what? Voltage times what? Current. We have power in different mathematical representation. Power, voltage times this. We have power also. V square all over what? Arrow in different types. And of course, we also have power in terms of energy in joules as what? Power, work times distance. In inverse is what? Then we can talk about work to be what? If this power, work all over what? Time. Time taken for you to carry out the work. Then we say, as you transpose, work will now be equal to what? Power times what? Time. These are basic expressions that we're going to use in carrying out our mathematical works. In terms of time, in terms of all that and all. So we have some examples and exercises you should lay your hands on in the material given so that you'll be able to familiarize with the basic designs and all that. So we looked at Ohm's law. That takes us to another section or lessons, Ohm's law. What is Ohm's law? Ohm's law states that the current I flowing through a metallic conductor or flowing in a steady or direct proportional, like we used to say in OKK, the old physics. So Ohm's law states that the current flowing through a metallic conductor is directly proportional to what? The potential difference, provided what? Temperature remains constant. So in all this, what is talking about? Directly proportional to voltage. So from here, mathematically, Ohm's law at a constant value, V is equal to what? I arrow. In transposing this, we have I, current, to be what? V all over arrow. And also, you can have it as what? R, V, all over I. These are basic mathematical expression when it comes to what? Ohm's law. There are examples and exercises we can lay our hands on in the material so that we familiarize ourselves with the design. Various examples. So this mathematically we can talk about. Then we're gradually going up to proper what? Installation works. Here we looked at what? Electrical power and energy. Electrical power and energy. When we talked about electrical power, of course, we've seen various type of power. Like I said, power is in watts. Power is in watts, which we know measured in watts. And I will say power, we have it in I square arrow. We have power in what? V square all over arrow. We have power in what? VI. Which are basic formulas for power. Then we now come to when it comes to electrical energy. Basically, in electrical energy, we say electrical energy, we refer to it as what? Power itself multiplied by what? Time. If the power is measured in watt and the time is in seconds, therefore, the unit of energy, which is watt seconds, you can say watt seconds or what? Joules. Watt seconds or joules. Basically, energy in joules, which we've talked about. And of course, we have energy also in kilowatts, depends on the unit, kilowatt hour, kilowatts, whatever. Basically, in our energy consumptions, when it comes to now, we are driving to installation proper when it has to do with what? Domestic or industrial electrical installations. That is where I'm taking this, driving it to. Okay? Because energy, it is what we consume. I believe in your domestic installation, you might have been taught power supplies. Of course, now, the in thing now is what? The prepaid meters. The prepaid meters that we use now is in what? Energy. The consumption rate is rated in what? Energy. Like you can see when you talked about what? Kilowatt hour. That is your, for those of you that have prepaid meter, this is what your meter at home is being measured with, rated with kilowatt what? Hour. And we refer to 1 kilowatt. 1 kilowatt hour is equal to what? 1 unit. Is equal to what? 1 unit. Like you can buy in your prepaid, you say, how many units? How many? These units are what we refer to as what? The kilowatt what? Hour. The consumption rate depends on the number of units you buy, determines how, once you are consuming, the energy that is being driven. We'll see that in an example and an exercise given in the material, how you can what? Consume. What consumes electricity. The types of, it can be what? Electrical equipment. You can see an example. They say, okay, we looked at, and let's look at one example so that we shouldn't just be talking blindly. Let's look at an example. From the material, we have an example. It said electrical equipment in an office takes a current of what? 13 amps. A current of 13 amps for electrical equipment in an office from a 240 volt supply. From a 240 volt supply, estimate the cost per week of electricity. Costs per week of electricity. Cost per week of electricity if the equipment is used for what? 30 hours. Time. Equals to 30 what? Hours. If the equipment is used for 30 hours each week. And 1 kilowatt of energy cost. 1 kilowatt hour of energy is what? What is the cost of 1 kilowatt of energy? 25.7 naira. This is a unit. So what do you do? Here, the power, which we said is what? Is VI in watts. We're given what? Voltage and what? The current. The voltage we said what? Is 240 multiplied by what? The current, 13. That gives what? 3120 watts, which is approximately 3.12 kilowatt, which is 3.12 kilowatt. So energy used per week, it has to do with what? Energy per week. Energy consumed per week will now be what? Power times time. P times what? T. And of course, we have P to be what? 3.12 kilowatt multiplied by what? The time. The time we say is what? It's 30 hours. 30 hours. So therefore, this gives what? 3.6 kilowatt hour. And of course, the cost has to do with what? 25.7 naira. 25 naira, 7 kobo per week. So you multiply the energy per week by energy per week will be equals to what? 93.6 multiplied by what? 25.7. What does that give? That gives 2 naira. That will give us what? Equals to 2 naira what? 2,405 naira. 0.52 naira. What you're going to be consuming. So it depends on the unit you buy. This is how you calculate it. And your rate of consumption, if there is a regular power supply, you'll be consuming this amount per week from your prepaid. So most of you know what you are consuming in your prepaid and what you use. So this is how it is being calculated. You see more of the examples and exercises and the material. So from there, we looked at resistivity. Resistivity. What is resistivity and resistance? Resistivity and resistance. What is resistivity? Or resistance and resistivity? The resistance of an electrical conductor depends on 4 factors. Okay? 1, the length of the conductor. Length of the conductor. 2, the cross-sectional area. Cross-sectional area. 3, material type or type of material. Then 4, the temperature of what? The material. Temperature. So these determine, when you say the resistivity, because there are some materials that has high resistance compared to others. When you talked about the resistance of a copper material, is different from that of what? Aluminium. Different from that of silver. It's different from that of gold. Here we have various constant resistivity of different materials. Such materials we're going to be seeing in the materials, like we have copper, we have aluminum, we have carbon, we have glass, mica, depends. Then you can see most common that we normally use, which we're going to see in the material, and with some examples. Copper, these are standard what? Constants. These are constants. We have it as 1.7 times 10 raised to the power what? Minus 9. Constant material. That of aluminium, we have it as ohm meter. These are resistivity constants. We refer to it as what? Resistivity constants. Okay? So you see examples and how different types of material has different sizes or amount of what? Resistance. You see from the examples given and all that. Then, it now take us to the most important in design. We looked at types of circuits in the lesson. Types of circuits. Type of circuits. What are the types of circuits? Basically, we have two types of circuits. We have one, series circuit. Two, we have parallel circuit. And of course, we also have the combinational, but the combination has to do with both what? Series and parallel. In some materials, you can say combinational circuits, which is series, parallel circuits. But basically, like I said, two types of circuits. And of course, a circuit composed solely of components connected in series is known as what? Series circuit. While one connected completely in parallel is referred to as what? Parallel circuit. When you say a series circuit is a circuit from what we can see in the form. What makes this a series circuit is because it has same current. The same current flows from same current flows. Then the potential difference. You have different potential difference. When it comes to this, so you have different potentials. Voltage drops across each of the elements. This can be likened to an installation. Maybe when you want to do lighting installation. That is why you see some. It is not advisable to just have one switch controlling the whole, in a hall now, for instance, even in your room, one switch controlling the lights. Because if there is fault, peradventure, if there is fault in one, there will be, you carry out repairs without carrying out, without isolating that whole room or hall. So it has its disadvantage because same current flows through. And the elements or lights now determines how it drops if they are not of the same shape. We're going to see that in when we looked at some examples and exercises in designing of the series circuit connection, then you understand it more. In series connection, like I said, you have different voltage drops, V1 plus what? V2 plus V3. And of course, when it now comes to Ohm's law, we know that V is equals to what? I arrow. Okay? V is equals to I arrow. From there, in substituting this, we now have what? Arrow to be equals to what? V all over I, which we know. Then, expressing this I arrow, I arrow, I arrow. So basically, our total arrow here will now be arrow 1 plus what? Arrow 2 plus arrow 3. When you are now considering the total resistance, is the summation of arrow 1, arrow 2, and arrow 3. And when it comes to, this is basically what we use in calculating total resistance in a series connection. Then we looked at parallel. When we say parallel, is parallel connection is just an inverse parallel circuit. Parallel circuit is an inverse, which is basically advisable in carrying out lightning. You can see all the lights here. This line can simply be in series, but in parallel with the other series. So once there is a fault in any of these series connected lights, you can carry out repairs by isolating this particular row, and then while this is still on. But both this row is parallel to this row. So a parallel connection in the hall or even in the room is more necessary. Why we say it's parallel? Because it doesn't have the same current that flows through. Right? You can see. So you have it as current 1, 2. You can see that different current flows through, but same voltage supply. So in calculating this, basically we have it as 1 all over RT is equals to what? 1 all over R1 plus 1 all over R2 plus 1 all over R3. For parallel connection. You understand it better when you are substituting value from the example or exercise given which you are going to carry out before the assessments or exams, because we are going to carry out this design practically when it comes to the practical sessions, using this design to determine the amount of current that can flow through a particular room or hall in installations. So we're going to make use of this formula. Of course, when they are two, basically, you see that more in the course of carrying out our practical. So basically, what this implies is that from these two connections, series and parallel, we can draw out our what? Electrical installations that have to do with lighting arrangements. When it comes to lighting arrangement, we should be able to carry out this parallel series or even sockets. Even sockets. At times, you can decide to connect a socket in the room and you link the socket, a cable. You want to minimize. Carry a cable, once it's supplied, you loop from one to another. if there is a fault in one particular socket, it will affect others. So you have to put in them in parallel. You have to be in series and in parallel to others, so that when there is fault, the essence is that when there is a fault in a particular socket, that socket will not affect another because you're going to make use of it. So you have a tendency of isolating the particular socket that is same current pass through. While you carry out repairs on that, others still what function. So in electrical installation work, you should learn how to bring in the principle of what series and parallel arrangement. And of course, like the consumption rates in energy and power, we have calculated, we have looked at. We're going to see more in terms of what practical. Thank you very much for listening.